Okay, let's start. Good day, my name is Anne, and I would like to present our research. I will talk about some unusual field of geomorphometry application. We will speak about topography of silicon wafer and wafer-based structure. I work in National Research University of Electronic Technology in Moscow. It's both a scientific and an education organization. We develop some new microelectronic products, manufacture them on the technological line, and then we carry out research and testing of the manufactured structure. I will talk about the study of microelectronic objects, mainly silicon wafer and structure based on them. Please look at me. Here you can see plastic box and silicon wafer inside. Go to presentation. The characteristic dimension of the wafer are a diameter of 115 millimeters and thickness of about 700 microns or less. For formed structure, the planned dimensions are usually several millimeters. The height difference is no more than 10 micrometers. The purpose of analyzing the surface of silicon wafer is usually to determine their deflection and mechanical stress and their distribution over the surface area. The influence of the technological process on the topography of the surface is also investigated. This can be formation or removal of a layer, annealing, or any other process. When we talk about the control of formed structures, in our case, it's the most often the MEMS structures, that means microelectromechanical system. We speak about shape analysis, determination of mechanical stress and effects. So studying topography, it's a common task. This task we usually carried out using digital elevation models of wafers and structures. We obtained them by optical profilometry. This technique can be used to measure elevation difference up to nanometer range. The equipment and measurement technique allow one to obtain DEM of objects ranging in size from 47 micrometers by 63 micrometers to 3.4 millimeters by 4.6 millimeters with a DEM grid spacing from 98 nanometers to 57 micrometers. Using a stitching approach consisting in drawing a series of separate data frames, we can form DEMs of larger objects. However, this requires some post-processing of the DEMs. In our case, it's recovery of missing data and smoothing. I will talk about the result of using geomorphometry methods to process the obtained DEMs of several typical structures. The first is the topography of wafer surface. In this case, it's a silicon glass structure with a diameter of 150 millimeters and a deflection of about 20 microns. We obtained raw measurement data from the sample with resolution 57 micrometers, and after processing and smoothing the raw data, we reduced the grid spacing tenfold. So the morphometric maps display a complex shape of the generally convex silicon glass structure. For example, you can see the saddle area, which is a blue area on Gaussian curvature map, where this curvature is less than 0. The generally convex structure has 8 hidden micro-ridges, diversion, and 8 microslopes of different orientation. Such a CT fish-like shape of the structure surface is best revealed by the map of aspect and catchment area. A similar approach was used to analyze a silicon wafer before and after deposition of a silicon oxide layer on it. It's known that the formed layer leads to change the layer shape. It generally becomes convex or concave, but using geomorphometry methods provide more detailed analysis. The use of catchment area for analysis make it possible to trace the change of the position of micro-ridges. width. And you can see that the boundaries of the microreach are not changed their position. They are shown it with slight bicoloring arrows. Another example, it's a mechanically polished silicon wafer. Analysis area has a size of 0.23 millimeters by 0.17 millimeters and an elevation range of about 20 micrometers. You can see large furrow-like marks of mechanical polishing of elevations and on mean curvature. But mean or topographic form within each individual furrow can be found on the maximum and minimum curvature map. This slide shows the use of geomorphometric modeling to identify small linear defects by the highest value of the maximum curvature. This you can see extended convex region. And by the smallest value of minimum curvature, this, you can see the extended concave regions. Together, they constitute an extended linear defect. This approach we use to analyze other various structures. That's different membranes, cracking area, microtopography. We use geomorphometric modeling for localization of multiple defects and for their detailed analysis, and for many other goals. We analyzed maps of Gaussian curvature, mean curvature, principal curvature, non-sphericity, difference curvature, and many others. We used landlord software and MATLAB environment. The results shown that geomorphometric modeling allows us to derive digital models of morphometric variables from profilometer-based DMs with micrometer range, elevation difference, and resolution to reveal local concave and convex areas, to increase visibility of our data, to visualize area of linear defects, local bumps, and hollows. So that's all what I wanted to tell you. Thank you for your attention. If you have some questions, you can ask them for me or for Igor Falansky. That's all.